Okay, and we move to a completely different field. It's galaxy formation simulations in the exascale computing era. And the speaker is Claudio Dalla Vecchia from IEC. Okay, I will let you know after 23 minutes, okay?
Hi everyone, and thank you to the organizers for inviting me. So I was asked to talk about this specific technical topic. I will try to make it a bit more accessible than what it sounds in the title. Starting with the definition, exascale computing area is basically the next generation of supercomputers that will be able to run at exaflops speed. And one exaflop is 10 to the 18 floating point operation per second. So just to put it in human terms, is what, I mean, your laptop to do a second of computation comparable to this would take something like 100,000 years, and these computers can do it in 1 year. So, but I come from mostly galaxy formation and the development of models for galaxy formation. And before continuing to the topic, I would like to point you at this article that Gustavo Yepes and I wrote for the Boletín de la SEA, the last issue, which is about the computational astrophysics in Spain, its evolution since the installation of the first supercomputers in the Barcelona Supercomputing Center. What is the connection with the European strategy for supercomputing, and what are the challenges for the future, right? So it's a pretty long article, but I mean, if you dare to read it, it's a good read. So, as a general introduction for, so why do we do galaxy formation simulations, and what is the motivation? And I think the main motivation is that observations can observe a lot of galaxies, and but they are like frozen in time, right? So you see a galaxy, and you don't know anything about its evolution. I mean, you can infer from properties of the galaxy what happened in the past, but you don't see its evolution. You see just a picture. It's like taking a picture of a 30-year-old person. They give you a picture, you see the picture, you infer, well, it should be 30-year-old, but you don't know how this person was when she or he was a kid, and you don't know how it will evolve later. You can guess that because you see galaxies at different times in the universe, at different times of their evolution, but you don't see the same galaxy at different times of their evolution. So what a simulation can give is following the evolution time of the assembly of galaxy, of each galaxy that you have in your volume. So we talk mostly about simulation cosmological volumes that are used basically for comparing the properties of galaxy populations, like observed by large surveys. There are other type of simulations, zoom-in simulation, maybe you know a bit about them, that focus more on single objects or their satellites, the Milky Way, or a dwarf galaxy, or a cluster of galaxy, but just single objects. They are both cosmological, but these are volumes that are filled of galaxy everywhere, right? And going on, just a very brief summary of what these simulations are. So these are volumes, periodic volumes, cubes of this size. This is from the TNG, a nice illustration from the TNG, latest TNG simulation. And they can have different sizes, right? So right now, more or less, what is used as a good compromise between volume size and the resolution, this is the resolution, is around 100 megaparsec. Resolution, spatial resolution is around half kiloparsec. Gas mass resolution is around 10 to the 5, 10 to the 6 solar mass, that translates also in stellar mass that can be resolved, and dark matter mass is about this. Okay, there are already efforts to go beyond that, but let's take this as an example. And what does it mean if we wanted to simulate, for example, a large number of clusters? We would need to go to a much larger volume and to sacrifice a bit the resolution, normally, to be able to run it in a time that is comparable to the time this simulation has been run. We can also go to much smaller scales and try to go on to resolve smaller galaxies, and this usually is done by decreasing the size of the volume, maintaining the same number of particles, increasing the resolution, and taking more or less the same time of this, right? So this is a bit the idea, the basic idea. It's not all like this, but if you go to larger volume, the resolution decreases, right? So this is a list of things that are now basically in all codes, maybe the last two no, but all codes that are modeling galaxy evolution have to take into account gravity for sure, because it's the driver of structure formation, hydrodynamics to describe the thermodynamical state of the baryonic gas, gas cooling, which is also a very important thing, especially connected to chemical enrichment of the gas, and line cooling and molecular cooling, star formation, which is driven by gas cooling, and then all what we put in a big, under the big umbrella of feedback, which is anything that is returned to the gas phase, in form of energy, in form of chemical enrichment, in form of non-thermal pressure from magnetic field, cosmic rays, or in form of radiation for the few simulations that are able also to follow radiative transport, right? So all these, each one of these would need at least one talk or two each to be explained. But I mean, there are a couple of very interesting reviews that you can find in the last years that came out, and I was, yes, it was interesting to see that the word challenges appears 2 over 3 times, and this is a sign that the field is really young. People expect from simulation amazing things, but it's 30 years, more or less, that we are able to do galaxy formation with numerical simulation. So just to go back to what is the resolution and the need of resolution, this is a quite old plot, but it's very illustrative. This is star formation rate density, so it's the star formation rate per unit volume in one of these cosmological simulation, as function of redshift or time. And the points are observations. These are pretty old recopilation of observation. Now, we know that JWST is putting points here on this side, quite high star formation density at high redshift. But this is the effect of resolution. Resolution increases in the simulation. These are simulated star formation density, star formation histories coming from this from the evolution of galaxy in these volumes, and the resolution increases this way. So you can see that increasing resolution, the onset of star formation is at earlier time, or later, or higher redshift. You can see the same thing here. This is what we call merger tree, and it's a picture of the assembly of the mass of one main galaxy, which is moving on this line. Color is of the points is the stellar mass, and time is going from the bottom here up here. So this is redshift 0, and this is redshift 10. And here you can see, you can reconstruct all the mass assembly and where all the mass, stellar mass that ended up in this galaxy came from, right? There is stellar mass produced in situ, and then there are mergers with satellites. And you can see that the first satellites here that are, around this mass, so the limit of the resolution of the simulation I showed you before, are formed around redshift 10.9, right? So this is very interesting, because this simulation were expected to explain JWST finding, but it's very clear that we have to go to larger, higher resolution to be able to get galaxy forming a bit earlier and the onset of star formation a bit earlier. Curiously, if you look at this envelope, it goes like this. So the expectation is that it goes through what is observed with JWST. And the other thing that is needed is a larger volume. At high redshift, first galaxy form on the higher density regions, the higher over densities, and to be able to capture these galaxies that are forming earlier than other, the volume of 100 megaparsec may be too small. So one should go to larger volume and higher density, which is the challenge of all the simulation, or the models we are running. So this shows where we are right now, more or less. This is a list of simulations. These are the dark symbols are all hydrodynamic simulations of volumes that produce galaxies. And this is the open symbols are all dark matter simulation, so only gravity. Here you have, on the x-axis, the box size of the simulation, and on the y-axis, the mass, or let's say the resolution of the dark matter particle. Higher resolution is on the bottom, right? And these lines that you see here tells how many particles are in each volume, for each volume at a given dark matter mass. And you can see we are here with the hydrodynamic simulation, a bit better and larger volume with n-body simulation. So the idea is to move perpendicular to these lines, increasing resolution and increasing box size with time. Okay, so this needs more computer power, which is what I'm going to talk now. Needs for numerical code able to scale on a very large number of cores, which is a very challenging thing, and that depends on memory and load balancing that the code have to solve, especially load balancing. So being able to distribute the workload, the calculation on 100,000 cores, and not having 10 cores running calculation while all the others are waiting. This is a very challenging thing to do, and there are some solutions. But before going to the solution, this is what we are now planning at European level with the Euro HPC joint undertaking, which is an initiative of EU countries and companies, right, to develop a supercomputing ecosystem in Europe. It's the substitute of PRAISE, what was the previous consortium financing supercomputer. The plan is to install these exaflops capable supercomputer, and 3 pre-Exascale supercomputers have been approved and installed, and they are now running, and I will show you what they are. And then the interesting thing is that machine learning, artificial intelligence, move towards the architecture using GPUs, right? So GPUs are very, very efficient for machine learning, artificial intelligence. So now all these supercomputers to achieve this extraordinary compute power are using GPU. GPU have another important properties that they can do much more computation for much less, using much less energy than normal CPUs. So they are also more efficient energy-wise. So the three computers that have been approved and installed are these: Lumi in Finland, Leonardo in Italy, Mare Nostrum in Spain, at the BSC. Lumi has a capacity of more than 500 petaflops, so half an exaflop, and Leonardo and Mare Nostrum around 300 petaflops, right? So just a quick summary of the characteristic of Mare Nostrum. There are 2 partitions, well, there are 3 partitions, there are 4 partitions, depending on the day you look at the website. These things are added every day, but there is a general purpose partition with the 718,000 cores. It's just a CPU based. And then the accelerated partition that has almost 4,500 GPUs installed. And then general purpose, this is already looking forward in time, the new NVIDIA Grace CPU that are ARM CPU with GPU included in the same chip. And then there is a next one that on the website they say, well, we cannot say yet. Okay, so these are installations that are done for testing new hardware and the possibility of installing next supercomputer using this hardware. One of the challenges of all this is that GPU-based computers can have GPUs of different vendors. So Lumi has GPU from AMD, Leonardo and Marinostro from CUDA, and they are not compatible. So there is still a big problem, big challenge is the compatibility. There is not a real standard. So each vendor has its own compiler, its own libraries, etc. CUDA from NVIDIA is the most used, so we are on the safe side, at least here in Spain. But it would be almost, very difficult to change a code to put it on this supercomputer in Finland. It's a lot of time to do that. And talking about public numerical codes, and here I'm only talking about codes that have a full galaxy formation model, right? Already in things. And these are three very advanced codes. One is Swift, which is task-based, use task-based parallelism, and it's a way to overcome the problem of load balancing I was telling before by breaking in tasks that are studying the interconnection between different tasks, the calculation, right, and distribute that through a library through cores, and keeping all the cores busy in doing calculations, so there is no wasted time. Changa uses a similar thing using the Charm++ library, mostly for dynamic load balancing, which is what I was talking here, more or less. But they also support for GPU. So it's already on the side of the new supercomputer that I installed. And PKD Graph is an MPI multi-threading and GPU-based embody code. And I say embody, and some of you know PKD Graph because they are in Euclid. The Euclid flagship simulation was run with this code, and the volume, this is an embody, so only gravity volume was containing 2,000 billion particles, right? So it's one of the largest simulation ever run, embody simulation. It was run on 4,000 GPUs on Pizznight, which is a supercomputer of the National Supercomputing Facility in Switzerland, and it took 8 hours, so a bit more than 3 days. So it's a very, very well-optimized code. But as I say, it's embodied. So why I put it in the list of codes with galaxy formation models? Because we are at the IAC, we are working on that. So in collaboration with Douglas Potter, Joachim Steidel, who are the main developers of PKD Graph, we had an agreement with them that we were adding hydrodynamics solver galaxy formation model. For now is based on the Eagle simulation, but it can be whatever. And we are starting to put in relativity transfer. So they were very happy to collaborate with us. Everything we are producing goes in the public version of PKD Graph 3, right? I'm not saying go and use it because there are still some things to fix in the code, but we are at a good point after 6 years of development to have the code ready for running. And lately, we expanded the collaboration with Jose Antonio Pascual and his students. They are from San Sebastian. They are engineers, and they were looking for an application for GPUs. And so they offered to do a porting of the hydrodynamics to GPU. So we start to have already gravity and the embodied part, hydrodynamics on GPU, and later I hope, the relativity transfer on GPU. So the good thing is that, PKD Graph is released under open source license, and we kept everything under open source license. So everything we put in the code is available for free, basically. So in summary, I gave a brief introduction to cosmological simulation, motivated the need for large volume and higher resolution. You have seen this. I gave an example with the high redshift universe, but there are large surveys, if you think of, for example, Euclid, that are observing a lot of emitting line galaxies. So these, are large volumes that needs sufficiently high resolution to account for all the galaxies observed by this survey. The European effort, is to provide exascale compute infrastructure, and then, it's mostly motivated by machine learning and artificial intelligence, but we can take advantage of that. And there are many other applications, not only in astrophysics, that can take advantage of this kind of infrastructure. So we are on a good side here. There is a lot of money put there. There is a lot of effort mostly because of the people are scared of AI. So Europe wants to be at the forefront also in this. And for us, it's a good thing. And there are only a handful of modern cosmological cores, as I say, that can be efficiently used, but there will be more coming. For sure, there will be more coming. Developing this kind of cores takes years, right? So, only a few years ago, it wasn't really clear what kind of architecture were going to be used for the next generation supercomputers. GPU were not the most appreciated for the problem I said of compatibility and standard. But then thanks to artificial intelligence, now we have that. And that is all.
Okay, thanks, Claudio. Okay, we'll have time for questions. There, please.
Could you comment on how do you expect that the new generation of numerical simulations is going to solve the apparent tension between the number of galaxies, a very high redshift that the James Webb seems to be observing, which was the motivation of all the talk. So are you going to solve the problem? What the problems are? Are the problems in the code? Could you comment on that?
Yes, I don't know. Maybe there is some physics missing. Maybe the model needs some adjustment. But this points to the really points to the, how can I say? Really points to the fact that the problem may be only resolution in the current simulations. So when you try to compare high redshift observations, you don't have a simulation that can reproduce those high redshift simulations. You are not in the regime for this kind of simulation. Is that the question? Because I kind of.
So going a bit further in this question, it seems to me that the observers, every time we put a new telescope on the sky, it seems that it surprises, the universe surprises us, and the evolution seems to be much quicker than what we expected based on these simulations. You're putting all the emphasis on the resolution, but there should be some physics behind that continuous surprise of the universe to our eyes. Maybe some missing dark matter properties, maybe primordial black holes, but it seems to be that there should be some physical reason, not just technical limitations of our computers.
So one thing, there could be. I'm not saying that there cannot be. What I think is that from one side, we should wait a bit more to have more statistics from these high redshift observations and see, because some of these points that you see, here moved a lot with more observations. If you look at this plot now, this is much thinner. There's much less scatter here and much less scatter here, and many more points here. So, in part, I would like to see more data from the high redshift universe to see the thing. Then I'm a bit worried that there is a bias in the observations because when you observe the most luminous objects, right, the bias could be that they are forming in the highest density regions. And highest density regions, evolution is faster, right? It's generally faster. So galaxy evolves a bit faster than, for example, at the average density of the universe or in a void. So that's why it would be interesting to have more volume, more objects, and try to see if then something changes. But I agree with you. There could be more either need of more better modeling of the physics that we know. Going to say that maybe we need more physics or different. This I don't know, right? But it's a possibility.
Yeah, I would like to know your opinion on how long it will take for quantum computing to replace this binary-based GPU computing. 10 years, 20 years, a little more than that, less than that?
I don't have an opinion. I would say on the order of 10 years, right? But I mean, these things, if you just look at how machine learning from nothing became grow exponentially, I don't see why quantum computing cannot resolve some of the challenging problems, technical problems that it has, and just explode in the next few years. But I would say 10 years. It's challenging. It's challenging, I mean, technically, to keep processors at 4 millikelvin.
Any other questions? Okay. Thanks a lot for the last one. It was going to be my question also then. Okay, good. Then let's thank again the